So for this question, we have a rod that's an L shape coming out like this. At one end of the rod, at point B, there is a cable connecting it back to point C. And then at reaction A, it is a sleeve that fits through a square rod. So it can slide back and forth along this square rod, but it can't rotate. So it has resistance of moments in the X, Y, and Z direction, and it can move along the X axes, but nowhere else. So the question is this. Member AB is supported by cable BC and at A by a square rod which fits loosely through the square hole at the end joint of the member as shown. Determine the components of reaction at A and the tension in the cable needed to hold the 800-pound cylinder in equilibrium. So this cylinder is 800 pounds pointing down. We need to know the tension in this cable BC by cutting it, and also know the reaction at A. So the free body diagram I would use is creating this rod 3D. I think it might be helpful to show it 3D like this. And there is a force from the cable. I'm just going to kind of either cut the cable, or we can also just say this force right here, FBC. I will use coordinates just to make it very clear. So we have 0, 0, 0 here at the middle, point A. Then we travel, so to get to B, it is -3, 6, and 0. Point C, it is going to be 0, 0, 2. And we also need the unit vector from B to C. So let's start by defining all of the reactions. We have a reaction here going down 800 pounds. And then at the end here, we will make this clear with the X, Z, and the Y-axis. So there is an AZ, and we said there's no AX because it can slide along that direction, but there is an AY. And for the moments, we're going to draw them. I'll try drawing them in this color. There's, with the right hand rule, we're going to say the curl of our hand is like this, and our thumb points that way. So that means our fingers are curling that way, and our thumb is pointing up. This will be in the positive direction of Z. So we'll call this MZ, but we can call it moment at A, but in the Z direction, positive Z direction. Then we have a moment in the Y direction. So if my thumb is pointing that way, that means my fingers would have curled like this. So this is the Y, positive. Our curl would go like, fingers go like that. That is MAY. And it can also be counteracting this force. We'll just predict it. So instead of this AY pointing outward, we'll do the AY pointing the other way. So probably this way, because you can kind of guess this force, the cable's pulling back. So we want to counteract that with the AY pointing the opposite way. That means my curl also will change. So I will make my curl using the right hand rule again. It's the opposite way, that way, because my thumb would point out like that. That means my fingers will kind of curl like this. Okay, and the last one, we want to curl in this positive X direction. That means we will want our thumb to kind of go this way, and our hand curls that way. So the fingers, if you can imagine them, they kind of curl around that way. And I can represent that with a moment like this, with that arrow, but I'll call that MAX. So we have 3 moments, and then there's a couple of reactions here as vectors. Let's start by defining this FBC. So FBC is FBC times a unit vector. That will be, we don't know what FBC is, but we're going to do this whole deal from B to C. We have 0 minus -3, which is 3, 0 minus -6, which is -6, and then 2 minus 0, which is 2. All of that, so we'll call it I, J, K. All of that divided by square root of 3 squared plus -6 squared plus 2 squared. So all of that will be FBC 3 over 7 I minus 6 over 7 J plus 2 over 7 K. And we have our FBC. Now we'll use the equilibrium equations. So we want to find the reactions in that tension in the cable again, we can do sum of forces x, y, z. So going through sum of forces in the x, that means we'll take the x component of, there's FBC x component, and then there's no x component anywhere else. We'll do 3 over 7 FBC equals 0. So I'm taking the x component from this vector here, equating this part equal to 0. That means FBC equals 0. Let's do the other equations. Sum of forces in the y equals 0. So again, let's look at the y's. There is a y. There's also this y component of FBC, but that was 0. So we got AY equals 0. Then sum of forces in the z direction, we have AZ, and that will be pointing up. Then we have a minus 800 pointing down. AZ equals 800 pounds. Now we'll take the moment, and we'll take it at, we'll take the moment of x. So along the x-axis. I'll do it over here. Sum of moments about the x-axis equals 0. So along x-axis here, we have our moment in the x direction here, and we also have a moment caused by this 800 pounds, and then FBC we said is 0. So theoretically that will be like 0 times that moment arm, which is 0. So I'm going to focus on the moments that I see. There's 800 pounds times 6 feet. The right-hand rule will say fingers curl like that, thumb goes that way, and that is in the negative x direction, so negative. And then we have our MAX, and we assumed it's in the positive x direction, positive MAX. All of that equals 0. There's no other thing in the x direction, like these MAYs, MAZs are in the other axes. Okay, that means MAX equals 4.80 kip feet. That's that 800 times 6. I can make it into kip feet. And then let's do the other ones. M along the y-axis is 0. So we're now looking at y-axis. The forces here, there's FBC again, but that's 0. The 800 pounds aligns with that y-axis. And then we have MAY. That's the other one I see. MAY, positive, like we assumed. So for this last point, MAZ, there's a force pointing down, but it's parallel to the z-axis, so it doesn't cause any rotation. So if we have the z-axis like this, z, and then we have a force pointing down, there's no rotation along the z-axis. It has to be perpendicular to the axis. So we had the x-axis earlier, like this in 3D, force pointing down. There's a perpendicular distance to this x-axis, but there's no perpendicular distance in this case to a z-axis. So when it has a parallel force, that means there's no moment. And so there's no other thing acting in the z direction, so MAZ equals 0. So our answers will be here, MAZ equals 0, MAX equals 0, sorry, MAY equals 0, MAX equals 4.8 kip feet, and our force FBC equals 0. So that means in this cable, there's no force that is being felt in the cable due to this 800-pound cylinder going down. It looks like most of the reactions are happening at A, and the rotation happening is in the MAX direction. So this force pulling it down will cause the rod to rotate around this kind of, you can kind of tell if you draw it. It's causing it to fall down like this. That's happening in this MAX. That counteracts that falling. Then MAY and MAZ has no rotation along those axes, so there's no MAY, MAZ. That would be the answer.